Hey, this is Joe Foulds, and I'm here with Johnny Munro, and today we're going to be covering Irving's stable roommate matching algorithm.
What we're trying to solve is the roommate matching problem. This is where we have a group of people who are all trying to get a match with one other person in the group for a roommate. Each person must only have one match. There are no people left unmatched. It is also stable, so if it's unstable, there are two people who have not been matched with each other, but both prefer them to their current match.
So the stable matching algorithm is split up into two parts. The first takes the form of the Gale-shaped algorithm, and to set it up, you've got to get every person in the set to rank every other person in the set in order of their preference. Here you can see the group we're going to be matching: Alex, Bob, Chris, David, Evan, and Frank. Now obviously for the ease of this tutorial, we're going to go through and swap all of their names out for their initials. So first we start by getting A to rank everyone else in the set by order of preference, and then we follow through and for the same for B, C, D, E, and F, get them to also put the rest of the list in order of their preference.
Every person will take it in turns to propose in order of their preference. They will carry on proposing until they have a match. So if they've been rejected, they will carry on proposing. If a person's been proposed to and they haven't already got a match, they will accept that match. Or if the person is a higher preference than their current match, they will also accept that match and reject the others.
So here is a pseudocode explanation of the first part of the algorithm. We're going to presume that you're already familiar with the idea of pseudocode, and if not, we're going to link some resources in the description box down below where you can find out some more information. So now we're going to go through the table, and each person is going to propose to their most preferential person in order of their preferentiality. So to begin with, A is going to propose to C. Now obviously because C hasn't got a partner yet, C is going to accept this proposal, and we've noted down in the table below. You're going to follow through while we do this for the other examples as well. So B now proposes to F. F also accepts the proposal, so we've noted that down in the table below and circled the letter. Next, C is going to propose. Now C proposes to F because F is their most preferential partner, but unfortunately F has already accepted a proposal from B, and F prefers B to C, so F is going to reject the proposal from C, as we've noted in the table. As C is unmatched still, it's C's turn again. This time C proposes to D, which is its next most preferential partner. D hasn't accepted a proposal yet, so D accepts C. Now it's D's turn to propose. D proposes to A, and as A hasn't yet accepted a proposal, A accepts D. E's up next. E proposes to C. C has already accepted a proposal from A, and C prefers A to its new proposer, E. Therefore, C rejects E's proposal. E tries their luck again and proposes to their next partner, B. B is currently unmatched, so B accepts E's proposal. Next up, it's F's turn. F proposes to D. However, D has already accepted a proposal from C, whom D prefers to F. Therefore, D rejects F's proposal. Next up, F proposes to E. E is currently unmatched, so E accepts F's proposal. As you can see, the initial prioritization loop has now been completed. The pairs which have been crossed out can now be removed from the pair matching table, which makes things a lot easier for the future. To do this, simply remove the crossed out elements from the table and shift everything into the empty spaces moving to the left.
The algorithm will stop when all the proposers have now got a match. If there is one person who is rejected and they have no other possible people they can propose to, then it's unstable and then it will terminate. The Gale-shaped part of the algorithm is now finished, and we'll move to the second part. The second part contains two loops, of which the first loop is called preferable rejection. For each proposer's match, the match will reject any people who are less preferable than the person they propose to them.
We're going to start with the first match, which is D to A. Now, because A doesn't prefer anyone less than D, we're not going to make any changes to the table here. We'll look at the EB pairing next. Now, B prefers D less to E, so we're going to remove all DB pairings from the table. We'll now look at the AC pairing. If you look in the C's column, C prefers B less to A, so therefore we're going to reject all CB pairings as well. CD pairing up next, and as you can see, D prefers E less than the C pairing it already has, so therefore we're going to reject all ED pairs. Next up is the FE pairing. As we can see, E has already rejected everyone it prefers less than F, so we're not going to make any alterations to the table this time. Finally, we're going to look at the BF pairing. Now, F prefers A less than B, so we're going to go ahead and reject all FA pairs as well. Great, now that step's done. We're going to go ahead and fix the table just like we did before by removing all crossed out entries, and then shifting everything to the left to fill the empty spaces. Now onto the second loop of the algorithm. We're going to look through and create cycles in the table, and then we're going to go ahead and remove the pairs of diagonals. This might sound a bit confusing, but if you just watch how it's done, it's actually quite simple. So the pseudocode here shows the loop we're about to perform. As I've already said, we're going to presume that you're already familiar with pseudocode, so this doesn't need much explanation. Now we're going to create our PQ table. We're going to start with the A record, and we're going to select the second preferential decision from A. We're then going to select the last from that, the second from that, the last from that, and so on until we begin to form a cycle. We're going to select A's second choice, which is B. We're going to mark B off in the table as shown above, marked blue, and we're going to add B to the Q table. We're now going to go to B and select B's last choice, which is E. As you can see, we've marked E as blue in the table, and we've put it into the P section of the table below. Next up, we're going to go to E, and we're going to select E's second most preferential choice. As you can see from the table, that's A. So we're going to mark A in blue, and add A to the Q part of the table below. We're now going to select the last part from A's table, which is D. We're going to mark D in blue and add D to the P part of the table below. We're now going to go to D and pick D's second choice, which is C. So we're going to add C to the Q part of the table below and carry on to C. We're now going to select C's last choice, which is A. So we're going to add A to the P part of the table and continue on. Now we'll select A's second choice, B. However, from the table, B has already been selected, so we're going to colour in B red to show that we've reached the end of the cycle. We're now going to select diagonals from our PQ table, just like as shown in our explanation. The first diagonal we're going to pick is going to be the BE diagonal, shown below. We're now going to remove all of the diagonal matches from the table, which means we're going to remove all BE matches. We're now going to continue just like before, selecting the next diagonal, AD. Same as before, we're going to remove all AD matchings from the table. Just like before, we're going to select the final diagonal, which is CA, and we're going to remove all CA pairings from our table. We've now removed all the diagonals from the PQ table, so we're going to create another PQ table to find more cycles. Once again, we're going to start with A. Perform the steps exactly as before, but we're going to ignore all crossed out elements. So we're going to select A's second choice, which is now E. We're now going to go to E and select E's last choice, which is F. And we're going to select F's second choice, which is B. And B's last choice, which is now A. Now select A's second choice, which is once again E. As you can see, E has already been selected, so we're going to colour it red to show that's the end of the cycle. Just like before, we're going to remove the diagonal pairs. We'll start with EF pairing, and then remove the BA pairing as well. Great, that part's now done. So we can remove the marked off pairs from the table, and fix it just like before by shifting everything to the left. Brilliant, you're finished. You can check through this matching to see if all the matches provided are stable. We don't actually have time to go through all that in this video, but you can do it yourself easily by checking if any of the matched pairs prefer each other to their current match.
The next example is going to be where there's no stable matching occurring. So just a reminder of what non-stable is. If there's two people and they're unmatched and both prefer each other, then that is unstable. For this example is going to start off with A proposing to B, as that is A's preferred choice. B will accept A as it has no match already. B will now propose, of which he proposes to C, and as C hasn't got a match yet, he will accept, or she. C will now propose to A, and as A hasn't been proposed to, A will accept C's proposal. So D will propose to A, and he will get rejected as A has already accepted C, who's of a higher preference. So then he will go on to the next one and propose to B, who will get rejected again, because B has already accepted A's proposal, which is of a higher preference. Then he needs to propose to C, and he will get rejected from C, as C has already accepted B's proposal, who's of a higher preference. So he's been rejected by everyone, so no stable matching can exist for this group. So why is this unstable? So if D was paired with C, B would rather be with C, and C would rather be with B, so that's unstable. If D was with B, B would rather be with A, and A would rather be with B, so that's unstable. And if D was paired with A would rather be with C, and C would rather be with A, so D has no case of where it's paired up where it would be a stable match. And as you can see, the algorithm has detected this and worked out it's unstable.
We're going to make the presumption that you're already familiar with time complexity, in which case the time complexity upper bound is bounded by the worst complexity of any section in the algorithm. In Irving's algorithm, the time complexity of the worst loop is O of n squared. Therefore, the overall time complexity of the algorithm is bounded by O of n squared. There's a really good explanation about this in the analysis section of Irving's original paper, which we'll link to in the comments section below. Thanks for watching, we hope that was clear enough for you, and if there's any questions you have, please leave them in the comments section below and we'll address them when we can. Thanks again.